Hello folks, my name is Andrew Osipov. I'm the Principal Engineer with Cisco Security Business Group. And today I want to talk to you about one of my favorite innovation technologies, something that I've been involved since the technology was incepted, and it is called clustering. First of all, let's talk about why do we need clustering for security devices? What does it really mean? And to set that up, let's first talk about high availability and scalability. So you have two different kinds of technologies to provide redundant and scalable security services. So high availability is the most popular form of redundancy, and what it means is, well, I have my active firewall, and I also set up an identical device, and I call it my standby firewall. And they both hooked up to the same network. They both can see the same set of endpoints on the inside and outside, but only the active one is going to pass those connections at any given point in time. And for every active connection, for every connection that goes through this active firewall, it will synchronize a little connection record, a little piece of information to the standby firewall. So that standby firewall knows how to recreate the connection if something happens to the active one, if it fails, and the connection now switches over to the standby, newly active firewall. So this is something that pretty much all the security vendors implement in some shape or form. Some do a connection synchronization. You can just got the connection table being copied. Others replicate every single packet hit in the active firewall. So a packet comes into the active firewall, they copy it exactly as it is to the standby firewall. That's a bit suboptimal in my opinion, because now you're doing much more work than you would if you just synchronize the actual stateful record periodically. So that's high availability, right? Only one device is active at any given point in time. And now the challenge with that is most customers don't like to pay for idle hardware, right? Why would you set up two boxes, buy two boxes, and only one of them is actually doing meaningful work? So what also exists is the concept of high scalability. And high scalability is effectively trying to provide both redundancy as well as trying to move beyond just one box being active at any given time. Now, there are multiple approaches that the industry, most of the vendors take when it comes to high scalability. So some say, okay, well, we'll do something that's called the something that's called vertical clustering, right? Or vertical high scalability. So we take a big chassis, we populate it with many, many different modules, and then we vertically scale throughput by sharing the load through the firewall across all those different modules. How do they do that? Well, they typically, again, take the same approach they do on active standby. We'll just copy the entire connection table to each and every one of those firewall modules. So now, if you have one module which supports 10 million connections, guess what? This big chassis sometimes goes to 18, 19 rack units. This chassis still only supports 10 million across the entire set of modules. So now each one supports 10 million. You copy the same connection table to all of them, and you still have 10 million. A different approach to this is, well, let's designate one module in the chassis and make sure all the traffic comes into that module, and then that module will fan those connections out to everybody else. And again, you still have the same constraint, right? To statefully track those connections within the chassis, you still have to have those 10 million connections held here in a module that distributes the load, and then that module knows which other processing module has to process each and every one of those individual 10 million connections. So you do scale throughput to some degree in this setup, but unfortunately you don't really scale connections, concurrent connections, and connections per second. Now there's also horizontal scale and horizontal clustering, where you can set up multiple of those chassis side by side. So each chassis is vertically scaled, but you also combine those chassis into a single stateful cluster, and now you split the load between all those different chassis. And very, very few vendors actually do that. Most say, well, we'll give you vertical scaling or clustering within the chassis, and then we will do high availability, active standby between two chassis, and that's pretty much it. And this way you still scale throughput within the chassis, you don't scale connections concurrent and per second, and you obviously don't take advantage of this extra hardware in the second chassis, and you can't just deploy a single chassis because it becomes your single point of failure, and customers don't like a single point of failure when it comes to their enterprise network design. So these are your options for the industry. And most vendors, when they say clustering, they sometimes means this, high availability. Really, that's what the clustering solution is. And some mean, yes, there is some high scalability, but it's only this vertical scaling within the chassis, and you don't get much of horizontal scaling. So now let's talk about what our implementation of clustering in both ASA and Firepower Threat Defense Next-Gen Firewall looks like. We supported clustering since our ASA 5580, 5585 appliances. Now we also support it on Firepower 4100 and Firepower 9300 appliances with ASA, and the FTD inter-chassis clustering support is coming in about a month in our next software release. So how is our clustering different from all those different industry approaches? So first of all, we support both horizontal and vertical clustering at the same time. So you can have a 9300 chassis with 3 modules clustered together into one single logical firewall. Great. You can add one more 9300 chassis with 3 modules, ASA or FTD, and then extend your cluster to build one big logical firewall now of 6 modules. And you can go and do up to 5 chassis with 3 modules each in this big logical cluster, and every one of them, that whole big combination of chassis and module, will look like a single logical firewall, which is pretty cool. And we also provide fully distributed data plane. So what I mean by that is any module in the chassis can get a packet for radio connection and process it to completion without having to redirect things somewhere else, without having to replicate the entire connection table to everybody. It is all fully distributed. And how do we achieve that? Well, let's go through an example. Let's consider a cluster of 3 modules, just to be simple. 3 modules. You have those cluster members. You have your client here, standard application. You have your server on the other end. And we'll say this is your FTD cluster or 3 module. So when the client wants to establish a connection to the server, and we'll just assume it's TCP because it's more interesting, it will send the packet normal TCP. You look up your default gateway. Your default gateway happens to your FTD cluster, single IP address across all the cluster members. So it goes to this single IP address, and this is typically your Ether channel here, spanned Ether channel across all the different chassis, kind of like a giant virtual port channel from Nexus World. And the client sends a packet, TCP SYN, and it just so happens to hit a particular cluster member. Doesn't matter which module it is, which member it is, it just hits one of them. So that member is going to check its own local policy, hopefully permit the connection, and forward that packet on to the server. Now, one thing that this member does, it first of all becomes the owner of the connection. We have a special thing in clustering. We have per connection roles. So the owner of a connection is the first unit to get the first packet for the connection, and that unit is going to own the connection for its lifetime. Why? If you watched our flow offload video, I talked about how important it is in a stateful device to see every single packet for your connection in a single processing instance. So that's exactly why. We want to see every single packet for this connection on this one cluster member, so we can correlate all the context, all the packets, everything, all the stateful records, all in one spot. So this unit becomes the owner of this particular connection. And then as the owner, it permits, it sends the packet through. It also embeds a little piece of logic we call the TCP SYN cookie. So by default, we randomize TCP initial sequence numbers when packets come through us. And so as long as we're randomizing, as long as we're changing it, we might as well encode something useful into that field. So what we do, we actually encode within this random value, we encode the identity of this cluster member, we call it cluster member 1. So when this happens, right, sometimes it happens, your network's designed with redundancy, and sometimes that causes asymmetry. So when the TCP send ACK packet from the server back to the client hits a completely different cluster member, what this cluster member can do, it can look at the acknowledgement number in the packet, it can subtract 1, figure out the initial sequence number, ISN, and from that decode the identity of the owner unit which processed the TCP send. So now what this unit will do, it will become something we call a forwarder. Since it can't process a packet which belongs to a connection owned by somebody else, it will redirect that packet back to the owner over the cluster control link. It's an out-of-band control plane interface connecting all the cluster members. So now the owner gets the packet, now it can enforce the appropriate stateful checks and it can send it back to the client. So all good, right? But now what happens if the owner goes away? Where is the redundancy in this? So there is one more bit. For each connection, each possible connection, we take the hash of the source and destination IPs and ports, and we compute an identity of the flow director. And so happens, say for this particular flow, this unit 2, right, this is unit number 3, unit 2 is the director. And now what the owner does, it sends a backup copy of the connection to the director. So the director can use it for 2 purposes. First, if somebody else asks the director who the owner is, and everybody runs the same hash function, everybody takes the source and destination IP and port information for a connection, it can always figure out who the director is. So the director can tell that unit who the owner is, and if the owner goes away, then somebody else can recover this connection based on the backup flow data contained within the director. So that's kind of the secret sauce behind clustering, right? This is how we can not only scale throughput, obviously throughput is scaled, but also concurrent connections and connections per second, because we don't replicate each and every single connection to everybody in the cluster. We create this smart copy of the flow only on one additional unit. So again, as the clustering scales to 16 individual modules and 5 chassis, 3 modules each here to a total of 15, nice round number, all those parameters scale along with the throughput. And we can get to 400 gig of next generation firewall throughput. We can get over a terabit of standard stateful firewall throughput with this kind of technology. So that's clustering. And next time what we're going to talk about, we're going to talk about something else that's related to clustering, which is inter-site clustering. How you deploy a cluster of ASA or FTD between multiple different geographically dispersed data centers. So that's going to be our future conversation topic. Thank you for watching. This is Andrew Osipov, and have a good one.